Hey Chem 20s. Here we are already in chapter 8. Not that we're really following along with the textbook, but if we were, we would be in chapter 8. This is all about applications of stoichiometry. So the main applications that we're going to look at here are limiting and access reagents. So it's more of a real world sort of situation rather than the perfect world that we looked at before, as well as a little bit of a look into titrations. So the limiting and access reagents, what we're starting with today, should go fairly quickly. It's only realistically a couple new definitions and a new idea based off of gravimetric and solution stoichiometry. Now that being said, if you haven't had an opportunity to really practice gravimetric and solution stoichiometry, please go and have a look at the last couple of videos and try it out and make sure that you understand that before you jump into this, because this would be very, very confusing if you don't. Okay, so let's get into it here. Limiting and access reactants, or sometimes called reagents. Sometimes reagents, sometimes reactants. You just know that means the same thing. Essentially what we've talked about so far is this first bullet point. So the reactants react together and the reaction is complete and there's no trace of the reactants. They're said to be present in stoichiometric amounts. So in other words, the amount of reactant A plus the amount of reactant B perfectly reacts to make AB, the compound. So perfectly reacts. That's not very realistic. Usually we have more of one than the other. So we might have way more A than we have of B. And maybe we're going to have some A left over in the end, right? The reaction is complete. We've totally used up B. All right, that's fine, but it's not quite perfect the way that we're dealing with before. So our new definitions that we've got is we've got the limiting reactant or limiting reagent. There's that word reagent. That is the one that is going to be completely consumed in the reaction. In other words, there's going to be none of that one left, and it's going to limit how far the reaction goes. Because once you run out of it, the chemical reaction doesn't work anymore. Then we've also got the excess reactant or excess reagent. This is the one that you've got more than enough of. So there's going to be some left over when the reaction is complete. Now, one thing to kind of note with this is because of the mole ratios and because of the well, especially with masses, because you know that everything's got a different molar mass, the limiting reagent is not necessarily the one that you've got a less mass or even a less amount of. It's the one that will give you the fewest moles or the fewest amount or even the fewest grams of product, right? So don't just be like, oh, well, we've got 6 A's and we've got 4 B's. B is clearly my limiting. That's not necessarily the case. We have to look at that balanced chemical reaction and we have to figure out which one's going to make the least amount of product. So I say moles here. You could also say grams of product or mass of product. So let's explore this just a little tiny bit more. I'm going to do a super easy one before we get into other things. Super easy one. So you know how to make a bologna sandwich, right? You take 2 pieces of bread. So 2 pieces of bread. And you might make or take, let's say, 2 pieces of bologna. Bologna. Something like that. I don't know how to spell bologna, apparently. Okay, and then with that, you might have 1 slice of cheese, and that's going to make 1 sandwich. Now, if you're working for somebody, and you're working at like Fife and Nickel or something like that, you know, some nice local company, and they're selling bologna sandwiches, this might be the only way that you're allowed to make those bologna sandwiches. So this is going to be our balanced chemical reaction. That should, if it's a chemical reaction, be an arrow, not an equal sign. Silly me. So let's go through and let's just kind of think about this for a little bit. You're making these sandwiches. This is the way the sandwiches have to come together. Let's say that I had 16 pieces of bread, 8 pieces of bologna, and 8 pieces of cheese. How many sandwiches could you make? Knowing that they have to be in this ratio. 2 breads, 2 bolognas, 1 cheese makes 1 sandwich. Let's see. If you have 16 pieces of bread, the ratio is 2 to 1, so 16 pieces of bread could make 8 sandwiches, right? If I had 8 pieces of bologna, Well, each sandwich needs 2 pieces of bologna. That means that we could make 4 sandwiches from our bologna. And then from cheese, well, 1 piece of cheese makes 1 sandwich. That means that we could make a total of 8 sandwiches from our bologna. So which one is our limiting reactant or limiting reagent? Well, it's the one that makes the least. So with the bologna, if I had 8 pieces of bologna, I could only make 4 sandwiches. I'm going to have some leftover bread there, right? So the bread's going to be in excess. When I have some leftover cheese, the cheese is going to be in excess, and the bologna is going to limit how many sandwiches I can make. So the bologna is my limiting reactant or my limiting reagent. Cool, I hope that kind of makes sense for people. I'm going to clean this up. Actually, you know what, I'm not even going to clean that up. We'll just go down and we'll check out this quick thought lab on limiting items or limiting, I guess in this case it's items because it's not really, chemical reaction. So this thought lab, suppose you're in charge of a company that's manufacturing widgets. So a widget is a contraption that consists of 2 nuts, 1 washer, and 1 bolt. Their word equation is as follows. Very nice, very nice. So a bolt has the symbol BT, a washer has the symbol WA, and a nut has the symbol NU. Okay, so let's check it out. We can actually write a chemical reaction for this. Right? Chemical reaction. So 1 bolt plus 1 washer plus 2 nuts is equal to 1 widget. Cool. Or the diagram down below. 1 bolt, 1 washer, 2 nuts is equal to 1 widget. Kind of makes sense. That's the only way to make these particular widgets. So let's say that we are given 75 bolts, 100 washers, 100 nuts. How many widgets could we make with that formula BT, WA, and U2? Okay, so let's just go through and let's check this out. So 75 bolts, 75 BT. How many widgets can that make? Well, let's go back here to our chemical formula. 1 bolt can make 1 widget. Okay, nice. So that means 75 widgets. Nice. Okay, what about washers? Okay, I got 100 washers. Okay, and let's go back and let's check out our formula. 1 washer makes 1 widget. Okay, so that means if I have 100 washers, I could make 100 widgets. Good, good. And then I have, let's see, 100 nuts. I don't know why I didn't abbreviate that, but whatever, 100 nuts. Well, let's see what our ratio looks like here. Uh-oh, I think I went the wrong way there. Yes, I most definitely did. 2 nuts is equal to 1 widget. So I could even go through and I could say 100 nuts, and I could use my mole ratio here, right? Well, I guess it's not really a mole ratio, but I want to get rid of nuts, so they go on the bottom. I want to end up with widgets, so they go on the top, and it looks like 2 nuts for every 1 widget. So cancels out. That's very similar to what we've done before. That's only going to be 50 widgets. So we can go through which reactant limits it. Well, it's the nuts, right? You're going to run out of nuts. You'll only be able to make 50 widgets. Everything else you can make 75 or 100. Which do you have extra of? Well, you've got the bolts and you've got the washers. You've got extra bolts and extra washers. How many extra of each? Well, if you can make 50 widgets with 100 nuts, that means you can make 50 widgets. That means you're going to have 25 bolts left over. And let's see, I think you're going to have 50. So you've used up 50 of the washers. You're going to have 50 washers left over. That's not a very good W. What is the mole ratio of nuts to bolts? Well, we need 2 nuts for every 1 bolt. Similar stuff that we talked about. What is the mole ratio of nuts to washers? Well, it's still a 2-to-1 ratio, right? You need 2 nuts for every 1 washer. Cool. How does the amount of reactant that is present in excess affect the quantity of product that is obtained? Well, short answer is it doesn't, right? So this is the reactant that is in excess. It means you've got too much. It doesn't slow down. It doesn't stop it. It's just you're going to have some left over. That's all. That's all there really is to it. It does not affect the quantity. It's only the limiting reactant. So let's see. Question 3. In this case, there were fewer bolts than nuts or washers, but the bolts were not the limiting reagent or reactant. Can we explain that? Yeah, absolutely we can. And that's because it takes 2 nuts to make 1 widget. So even though there's more nuts, so even though more nuts, it's still our limiting reagent. We run out of those first. Cool. So this is the big idea here, right? It's what you run out of first. That's your limiting reagent. It's going to limit how much product you can make. And excuse me, anything that's left over is an excess reagent. It's not going to limit what you make at all, right? It's extra. It's excess. Cool. So that wasn't very chemy what we just talked about there. Not exactly very chemy. What we want to look at now is how we can relate this to actual balanced chemical reactions. Now the whole key with this is, the whole 100% key is the limiting reactant is the one that makes the least amount of product. Limiting reactant or reagent makes the least amount of product. So what you need to do, the easiest way to deal with this is to do 2 stoic reactions and figure out which one makes the least amount. Which one makes less product? Now, sometimes you might have 2 products, and the question is just what is the limiting reagent? Then it doesn't really matter which product you choose, right? The limiting reagent will make less of product A, and it'll also make less of product B. Sometimes it'll be a little bit more specific. It'll tell you how much of product B is going to be produced. And then you'd go through and you do 2 stoichiometric reactions, holy mackerel, reactions, that's better. And you just say, okay, well, which one's going to make less of product B? The one that makes less is your limiting reactant, and the amount that's less is going to be how much you actually make. So hopefully that kind of makes sense. If it really does, if you're really good with this and you're good, you understand, you could probably push the pause button here and go try some of them out. That being said, we'll look at probably 1.5 quick examples here just to make sure that we're good to go. So the first example, we're given a chemical reaction. Nice, it's just the formation of water from hydrogen and oxygen. We want to identify the limiting reagent in each, identify the limiting reagent in each reaction mixtures given below. That sentence was hard for me to read. So we got 100 molecules of water and 40 molecules of O2. Okay, so let's start with this. 100 molecules of water. Excellent. I want to, and actually let me just go back a tiny little bit because I got a little bit lazy there. 100 water molecules. And then I want to go through, I want to cancel out the water molecules. I want to end up with my product. Oh boy, what am I doing here? It's not H2O, it's H2. Okay, take a second, take a deep breath. Let's really focus on this one. So 100 molecules of H2. We want to figure out which one's going to make the least H2O. So I got to cancel hydrogen. I got to end up with H2O or water on the top. So hydrogens cancel with hydrogens. This tells me for every 2 hydrogens, I make 2 waters. So it's a 2-to-2 ratio. So it's going to give me 100 molecules of water. Okay, that's easy. Let's try out the other one. I've got 40 molecules of oxygen I'm going to cancel out the molecules of oxygen and end up with H2O. So again, we're figuring out which one makes the least product. So let's see, oxygen has one oxygen makes 2 waters, so it's a mole ratio of 2 to 1. So let's see, 40 times 2, well, that is 80 H2Os. So which one limits the reaction? It's the oxygen that limits the reaction. And how much are we actually going to make? Oxygen is limiting reagent. And if we were going through, we'd actually only make 80 water molecules. 80 water molecules, and we'd have some hydrogen left over. Okay, let's switch this up and let's look at part B. This one's all about moles now, all about moles. So same sort of idea. I've got 0.5 moles of H2. I'm going to multiply this by, in this case, now a true mole ratio. I'm going to get rid of moles of H2, and I'm going to figure out how much product I make. So moles of H2O. So let's see, that was still a 2 to 2 ratio back up in the original, oh, there it is, in my original formula or equation up there. So moles of H2 cancels with moles of H2, and I'm left with 0.5 moles of water. Excellent. Okay, let's try out the next little piece here. 0.75 moles of oxygen. 0.75 moles of oxygen. I'm going to use my mole ratio to cancel out moles of oxygen. And I want to end up with my product, moles of H2O. So that's going to cancel. That's going to cancel. Let's see, it was 2 waters for every 1 oxygen. So in this case, I'm going to multiply it by 2 over 1. So that's going to give me 1.5 moles of water. So in this case, my hydrogen is my limiting reagent, and if this reaction were to actually take place, we would only make 0.5 moles of H2O because we've got less product being produced from the hydrogen. So the limiting reagent makes less product, and it's just like we're seeing here, it's 2 separate stoichiometric calculations. Okay, where it starts to get a little bit tricky, let's skip over C and let's just go straight to D. Let's skip C and go straight to D. So we got 3 grams of hydrogen and 20 grams of oxygen. 3 grams of hydrogen and 20 grams of hydrogen. The grams are what typically confuse people because yes, 20 grams of oxygen is a lot more mass, but that doesn't necessarily mean it's more molecules or more moles. So let's check it out. Again, it's just 2 stoichiometric equations, and we're trying to figure out which one makes the least product. Which one makes the least product? So I'm going to start with H2. So I got 3 grams of H2. I need to figure out how many moles that is. So I'm going to use the molar mass, grams of H2 and moles of H2, so that grams cancel out. Now H2, hydrogen, is 2.02 grams for every 1 mole. Now I want to use my mole ratio to go through, and I want to figure out, okay, well, how many moles of water can I make? So again, it's that 2 to 2 ratio. So let's see, I got moles of H2, and I got moles of H2O, and again, it's a 2 to 2 ratio, so moles of hydrogen cancel with moles of hydrogen. And for this one, I'm probably going to need a calculator, so let's get out the old calculator. And I've got, how many grams was it? 3 grams. 3 divided by 2.02 times 2 over 2, which doesn't really change anything. So let's see, that works out to be 1.485. We wanted to do sig digs, we'll do 1.5 moles of water. Okay, cool. So that's with hydrogen. Let's figure out now with oxygen. So I got 20 grams of oxygen. I'm going to multiply it to get it into moles, so I have to use my molar mass. So let's see, grams of oxygen has to go on the bottom so that they cancel. Moles of oxygen need to go on the top. And let's see, it is 32 grams for every 1 mole, because remember we're dealing with oxygen, O2. And then I use my mole ratio here. So my mole ratio is, back up to here, 1 oxygen for every 2 waters. So let's see, get rid of moles of oxygen, end up with moles of water. So oxygen cancels with oxygen, and it was 1 oxygen for every 2 waters. Cool, okay, now I've got moles of oxygen. So it was, let's see, it was 20 grams. So 20 divided by 32 times 2. 20 divided by 32 times 2. This is actually only going to make 1.25, or with SIGDIGs, 1.3 moles of H2O. So if this chemical reaction was actually happening, where I took 3 grams of hydrogen and 20 grams of oxygen, my hydrogen is going to be my excess, and my oxygen is going to be my limiting reagent, because again, it's going to make less. And this is how much water we would actually make. So it's whichever one makes less product. Cool, okay, so still not exactly the hardest question. Let's try out one more full-on, tricky, kind of challenging one. Excuse me. So this is now, what page are we on here? This is page 4, okay. So we've got 15 grams of aluminum sulfide and 10 grams of water react until the limiting reagent is used up. Here's the balanced chemical equation. Nice, okay, that one's already done for us. What is the limiting reagent? What is the maximum mass of H2S, which can be formed from these reagents? So we're looking for the mass of this. Excellent, excellent. Let's start to summarize what we've got here. So I've got 10 grams of water, and we know that the molar mass is 18.02 grams per mole. Excellent. We've got 15 grams of aluminum sulfide. I have no idea what the molar mass of aluminum sulfide is, so let's just get out our little calculators. So aluminum sulfide is Al2, aluminum number 13, so 26.98 times 2, plus sulfur 32.07, and we've got 3 of them, so 3 times 32.07. Something went horribly wrong there. So 26.98 times 2 plus, I think that's the problem, 3 times 32.07. That's a little bit better. 150.17 grams per mole. And then might as well do the hydrogen sulfide as well. So I've got 2 water molecules. So that's 1.01 times 2 plus 32.07 for the 1 sulfur, 34.09 grams per mole. Okay, nice. So part A and B, we're actually going to answer at the exact same time. All we have to do is 2 stoichiometric equations and figure out which one produces least. So let's start with the aluminum sulfide just because it's first. Al2S3. Okay, so I've got 15 grams of Al2S3. Excellent. I need to turn that into moles. So grams of Al2S3 go on the bottom, so they cancel. Again, you can put that over 1 if you need to. And then moles of Al2S3 go on top. Now the nice thing is I've already written this out, so I know that that's 150.17 grams for every 1 mole. Nice. Now the next thing I need to look at, I'm not really concerned about the moles of aluminum sulfide. I'm more worried about the hydrogen sulfide. So let's cancel out moles of aluminum sulfide. And let's do our best to end up with moles of hydrogen sulfide. Awesome. I just got to look at the mole ratio. It looks like there's no number in front of the aluminum sulfide, so that's a 1, and there's a 3 in front of the hydrogen sulfide, so a 3-to-1 mole ratio, and the aluminum sulfide cancels. Perfect. Okay, next step is if I'm looking for mass, like I could stop here and figure out my limiting reagent, but I might as well take it one step further and just figure out the mass. Whichever one gives me less mass is going to be my limiting reagent. So I got to get rid of moles of H2S. So I'm going to put that on the bottom. I'm going to end up with grams of H2S. So I'm going to put that on the top. And then I just got to fill it in. So it's 34.09 grams for every 1 mole. We see the moles cancel. And I can go ahead and get the old calculator out again and just go, okay, so it was 15 grams. I believe it was 15. Yes, 15 grams divided by 150.17 times 3 times 34.09. Nice. And that will give me, let's see, with SIGDIGs, 10.2, I believe. So 10.2 grams of H2S. So if we had 15 grams of aluminum sulfide and unlimited whatever else, we could get 10.2 grams of H2S. Okay, let's try it out with H2O, and let's see what we can get with H2O. So we're starting out with 10 grams of H2O. We're going to multiply that to get moles. So grams of H2O has to go on the bottom. Moles of H2O has to go on the top. It's 18.02 grams for every 1 mole. Nice. Okay. Grams cancels, and I've got moles of H2O. Now I need to use my mole ratio to figure out how many moles of H2S. So moles of water go on the bottom. Moles of H2S go on the top. Moles cancel with moles. Just got to check out my mole ratio. So let's see. 6 and 3. So 6 waters make 3 hydrogen sulfides. Cool. Now I've got moles of hydrogen sulfide. My last step is actually going to be exactly the same. I want to get rid of moles of H2S and end up with grams of H2S. And it was 34.09 moles. Sorry, grams for every 1 mole. We see moles cancel with moles, and all I got to do is get out the trusted calculator. And so what was it? It was 10 grams. Okay, perfect. So 10 divided by 18.02 times 3 divided by 6. So that's my mole ratio. And then times 34.09. And works out to be 9.46 grams. 9.46 grams of H2S. So just checking this one out and just kind of figuring this one through, if I had 15 grams of aluminum sulfide, I would make 10.2 grams of hydrogen sulfide. If I had 10 grams of water, I would make 9.46 grams of hydrogen sulfide. Which one makes less? The water. So that means we are actually going to make 9.46 grams of hydrogen sulfide, and water is the limiting reagent. So whichever one makes less is the limiting reagent. Now this is a bit of a time-consuming thing, right? Figuring out the limiting reagent. Honestly, if you understand how we did the stoichiometry, so to figure out how much product is made from aluminum sulfide and how much product is made from water, and you understand that the one that makes less is your limiting reagent, and the lower value is the one that you're actually going to make, so in this case 9.46 grams, you're probably good to go, because the rest is, like, it's honestly the same thing over and over and over again with stoichiometry. It's all about canceling out the units. So if you want to get a bit of practice in with this, like honestly, you could probably do a couple of them, like 1, 2, or 3, and as long as you're getting an idea, you're good to go. There's a ridiculous amount of practice all the way up to, let's see, page 8. So page 8 that you could check out if you want to. But again, once you start to get the hang of it, and once you get the hang of those stoichiometric calculations, you're good to go for Chem 30, right? You know what a limiting reagent is, you know how to do stoichiometry, you are good to go. So I'll leave it with that. It's up to you how much you do, but please practice until you are confident. Anyways, that is it for now. We will see you again real soon, Chem 30s. Bye-bye.